Data comes in heterogeneous forms, such as graphs, tables, or raw text. It is often difficult to compare and analyze together those different data models ranging from very structured to totally unstructured. My name is Irène Burger, and in this presentation, I will describe the approach we have taken to overcome this problem in our paper toward visual interactive exploration of heterogeneous graphs. The work on this project aims at improving the usability of a tool called ConnectionLens. So let us first explain how it works. ConnectionLens is a tool designed for data journalism that provides a solution for exploring data sources with heterogeneous models using the following methods. Each type of model, here we have a JSON document, a text, and a relational table. So each of them is systematically translated into a graph that mimics the initial structure of the data. Then, the resulting graphs are merged into one single large graph by linking nodes that are considered similar, the same as edges represented in the picture. A named entity recognition module that identifies people, organizations, and locations is used to extract those entities from any text appearing in the graph, highlighted in yellow in the picture. For large data sources, the resulting ConnectionLens graph is too large to be visualized entirely. That is why ConnectionLens supports keyword search on this graph to be used by journalists in order to find relevant links, for instance, between people. This example contains datasets about politics. In the figure, you can see an answer tree to the query Macron color Costa. However, notice that some nodes on this tree are difficult to interpret, for instance, data sources nodes and structural nodes. In the paper, we describe a solution to simplify the ConnectionLens graph by creating a smaller abstract graph. It could indeed make the answer to queries more understandable and potentially enable the users to explore the entire graph at once. In order to abstract the graph, we concentrate on a few principles that we agreed on when talking with journalists from Le Monde, for whom ConnectionLens is designed. They are the following ones. 1. Rich entities, that is to say nodes that have a meaning and that are characterized by attributes, are desirable. The structure, such as the boundaries of the initial datasets or internal nodes representing maps and arrays, is less interesting. And finally, relationships between entity nodes are meaningful. That is what journalists actually work on. So in order to apply those principles on the ConnectionLens graph, we designed an abstraction algorithm. Our goal is to extract rich entities and links from the ConnectionLens graph to produce a smaller and clearer abstract graph. We first decided to concentrate on JSON documents, as it is, in our opinion, the most difficult model of data to abstract. We then would like to generalize this algorithm for other models of data. The algorithm consists in 3 distinct steps. The first one is to identify entity nodes, that is to say nodes that have a meaning by themselves, contrarily to structural nodes and attributes. Here, we focused on a closed-world approach. We take into account only the types of node extracted by the named entity recognition module as described earlier. It recognizes people, places, and organizations. The second step is to choose the nodes in the neighborhoods of these entities that can be considered as their attributes. And then the last step is to rebuild the links between those enriched entities. As for now, the first step in our closed-world approach is already provided by ConnectionLens. We will concentrate on the other steps. I describe here how the algorithm works on a JSON document describing Nobel laureates that has been transformed into a graph. So let us concentrate on one part of the graph. On the figure here, you can see the nodes that are entities. They are green with a black border, whereas values not recognized as entities do not have a border. Here, we look at the edge profession, which leads to researcher. That should typically be an attribute of an enriched entity. But which one? There are indeed several entities in the neighborhood of the node researcher, here Jean S and INRIA. So to decide which entity this attribute profession equals to researcher belongs to, we ask ourselves, what are we talking about here? Using the labels of the edges in the graph, here in particular laureate and name, we are able to detect that the map is about the laureate named Jean S. One of our goals is to make structural nodes disappear. Therefore, the node Jean S is pushed up in the graph to replace its parent, the map node. Nodes that are then children of Jean S but are not entities, for instance, researcher, become its attributes. We repeat this operation, gradually deleting structural nodes, especially maps, with a bottom-up approach. Once we have this intermediary simplified graph, we notice that we have managed to get rid of most of the maps. We then keep only the nodes that have been detected as entities and build links between them using existing paths of the intermediary graph, as shown in the figure. The labels on the new edges are a concatenation of the existing labels on the path. We have coded a first version of this algorithm. You can see it applied here on our toy example. Notice that it successfully transforms a JSON document into a small graph. So after this preprocessing of the ConnectionLens graph to make it smaller and clearer, we would like to provide a better way of visualizing it for users. Through an interactive interface, we wish to allow the user to populate incrementally an initially blank canvas with nodes of interest. For instance, considering only the neighborhood of specific entities, choosing to display one type of entity, show some attributes and not others. For example, some node attributes can be visually encoded using variables such as size, color, hue, saturation, shape, etc. The algorithm successfully reduces the size of the ConnectionLens graph. In the picture, G is the initial graph and EG is the abstract entity graph. We can see in the figure that the size of the graph is divided by almost 10 most of the time. However, we also notice that some information is lost in the process, the deleted nodes in the picture. Indeed, some nodes that are neither entity nodes nor structural nodes are not transformed into attributes because they do not have entity nodes in their neighborhoods. We understand that this is due to our reduced approach of the world. Not everything is about people, organizations, and places, even though it is a good starting point for data journalism. For this reason, we have since then chosen to broaden our perspective and let go of this closed world approach. Influenced by our work on JSON documents, we have decided to use a new strategy. We want to see data as a set of records corresponding to the maps in JSON that are groups of heterogeneous nodes that describe one thing, and collections corresponding to the arrays in JSON that are sets of similar things, without necessarily knowing what those things are. Our goal is first to set the boundaries for those records and collections, and then try to understand what the things described by records are about. Then, the user could choose how to represent each record and collection, as a table, as a single node with many attributes, etc. The advantage of this approach is that it generalizes better for other types of data models, and it is much more flexible. Every record does not need to be about a person, an organization, or a place. It can be about something else entirely to be understood by the user. Thank you for listening.